Okay, so good evening. We are here to discuss assignment number 4. In the last class, we discussed 3 questions, and today we will start with question number 4. So let me just. So my screen is visible and voice is clear, right?
Yes, sir.
So, so let me just paste question number 4. Here it is. Try to have a look at it and see if you can uh, guess the correct option. So it says if M is a extension of Q uh, adjoined with root 2 and iota. M dash is the extension adjoining cube root of 2 and omega. And M double dash is the extension adjoining root 2 iota and cube root of 2 and omega, all four of them. So then choose the correct options. First, last 3 at least, I guess you can see easily. Yes, Vivek, have you gone through this question? Which one you think should be correct?
Sir, I think option number 2
Option number 2, okay.
and the other is option 3.
What's the justification? Okay, what is M intersection M dash? First one is perhaps the most easier.
M intersection M dash, I think containing root 2.
So M is having root 2 iota. M dash is cube root of 2 and omega. I'll just show the picture, the tower for you. So M is something that contains the smallest field containing the root 2 and iota, and M dash is the smallest field containing cube root of 2 and omega, and M dash is such that it contains both that is q root 2 iota cube root of 2 omega. So M intersection M dash. So see, this is the smallest field containing root 2 iota and q. So do you think root 2 belongs to M dash? It contains uh, cube root of 2 and omega. It is not.
No, sir.
It is the why? Why is it so? Why it is not containing that?
Because clearly first element is root 2 and the Q containing cube root of 2.
See, this is the smallest field containing this, and what will be the basis of this? So this contains elements of the form A, plus b omega plus c uh, omega square, but its degree is 2. So perhaps no, omega square also you can omit because omega satisfies 1 plus omega square is equal to 0,
0.
right? So omega square is just minus 1 and minus omega. So it's linearly independent, linearly dependent, right?
Yes, sir.
So, but 1 and omega are linearly independent, and then
C cube root of 2.
cube root of 2 is linearly independent, and d its square 2 raised to 2 by 3.
Root.
Okay, and then you have omega. Uh,
Total, I think 6
f,
element, na, sir.
yes, f times omega 2 raised to 2 by 3, and such that a, b, c, d, e, and f are inside q. While see, one way to check that if root 2 belongs to that, then q root 2 should be a subfield of this.
Oh,
Okay, but that won't happen because
sir, what
see,
was the fixed field? Because normal extension is defined on fixed field, I think. So here, which of the following will be a fixed field here?
normal field extension it means it is a splitting field of certain polynomials. So over q it's written, na? So q is the base field, and then they are
It is also.
extensions of that.
Okay.
Okay. So for root 2 not inside m dash, you can check like this. So the first claim is root 2 does not belongs to m dash. So see, if root 2, okay, so m dash also you can think like that. So q, then you have q adjoining cube root of 2, and then you have m dash, right? So this is the real part, and this you are adding the complex root, that is omega, right? So if root 2 belongs to m dash, then since root 2 is real, root 2 can only belong to q cube root of 3, right? That's the only possibility because other part has the complex thing, correct? So what I mean to say ki this part is complex, this is complex, this is also complex b omega. So only a, c, and d can be non-zero, and they have b or e and f has to be 0, right? So from here also you can see that if root 2 belongs to m dash, then uh, root 2 belongs to R, and this implies that root 2 should be A plus C 3 2, and then D 2 2 by 3, right? Because other part is complex, it will make it a complex thing. Okay, so maybe this part I can erase. But can it happen? And this will implies that uh, root 2 is inside Q cube root of 2, right? And this implies that q root 2 is inside q of that, because q is already there. Clear?
Sir, no, sir. Green.
So shall I change the color? This color is not visible or what?
Okay. You can change, sir.
Now it's better. So see what is happening here. So our claim is root 2 is not inside m dash. So let's suppose that root 2 is inside m dash. Then since uh, since root 2 is inside R, the real number, right? So it cannot have the complex part. Omega is a complex uh, element, na? Uh,
Yes, sir.
so the coefficients of omega should be zero. Omega cube root of 2 and omega 2 root 2 raised to 2 by 3. So it should be of the form a plus some c times cube 2 cube root of 2 and then d times 2 raised to 2 by 3, right? For some a, c and d inside q, right? And that means root 2 is inside the q adjoined with cube root of 2. This is just q adjoined with an element of q adjoined cube root of 2, right? But as root 2 is there, q is there, so q adjoint root 2 will also be a subfield of this because it is the smallest field containing q and root 2. But can it happen?
No, sir. I think last
This is
statements will be false.
contradiction because uh, q root 2 has degree 2
Two
over q
cube
and q cube root of 2
degree
has
3.
degree 3 over q, and clearly 2 does not divide 3. If it's a subfield, its degree must be dividing it, right? So root 2 cannot be there. This implies root 2 cannot be inside m dash. The second claim is iota can also iota is not inside m dash. Then only we can say what is the intersection. So for iota, so if iota is inside m dash, then now iota is complex, purely complex, right? So since iota belongs to uh, the imaginary part of I should not write like this. So maybe this is the right way to write. Iota belongs to Q M dash. Then see this part is real. This part is also real, and omega also have some real part, right? What is omega? Omega is
1 plus root 3 I upon 2.
this is I will say cos 2 pi by 3 plus iota sine 2 pi by 3, right? Cos 60 plus iota 60 sine 60 or 120.
Yeah.
So this is uh,
Two.
minus root 3 by 2, I guess. Yes, cos pi
Nice.
minus,
Minus 1 upon 2
okay, minus 1 upon 2
plus I root 3 upon 2.
plus I root 3 by
2.
2. This is right.
Yeah.
So you put the value of omega there and you will find contradiction. If I belongs to m dash, then uh, I equal to a plus whatever it was, b omega, right? B omega c root 2 b minus 1 was there, right? Minus 1 plus iota root 2 minus 1 plus iota root 3 by 2, and then you have c times cube root of 2 plus d times 2 2 by 3 plus e times their multiplication. I think comparing the real parts only will give the contradiction. But let's just write it once. That's it, right? So compare the real parts.
A
Compare
minus B upon 2 plus CD.
the real and complex parts. Yes, you were saying something. What it is? A minus b by 2
B by 2 plus C
plus
cube root of 2
cube root of 2
plus D
d 2 2 by 3
square upon 3 minus
e
C 3 root
e
2 upon
cube root of 3 by 2 and
2
minus
minus
f.
F
This is equal to 0, right?
0.
So see, mm, now you can use this, that since 1, this and this are linearly independent over Q, right? Because they form a basis. Therefore, we just now compare their coefficients. So a minus b root 2 is separate. A minus b by b upon 2 is 0. Now what is the coefficient of, because here it is 0
Okay.
plus 0 times 2 1
It
by
will be
3.
C by 2. C by 2 is equal
Yes,
to 0.
right? You can write it like that, 0 dot 0 dot dot. Uh, and c minus e
Upon
by 2 is 0, है ना? And d minus f by 2 is 0.
0.
So you have 2a equal to b, or I will write
2
it.
C E 2
A
D.
equal to b by 2 is better. C equal to e by 2 and d equal to f by 2, right? This is by real part. What
Okay.
your complex part is giving you. This is by the real part, and your complex part is uh, root 3 by 2b. This is complex part. So root 3 b by 2 right? This part will come, and then you have here it is root 3 times 2
Cube root of 2 upon 2
e
e and plus f
cube root of 2 e upon 2. This was right, and then you have f. F is
yes
having
f root 3
root 3 2 2 by 3 f by 2 is equal to 0, right? This is right. I suppose this is right? This is okay. So uh, this is 1. This is 1 iota na? This is 1. We are comparing the coefficient complex part. So this is equal to iota, so
1.
1 will come, right? Now can you say something?
So b by 2 is, can we change the name again from equation 1? B upon 2
Here
e upon 2 f upon 2.
that you can change, but it won't like b e and f. You're getting relation in b e f na, and here means they are also different. If something would have come from these pairs, then it would have helped. You can say root 3a plus e by 2 also you can replace by c, f by 2 also you can replace by d, but it won't matter as such. The problem will arise here only. And what is the issue here? So this implies uh, you can take root 3 by 2 common. This is b plus um, root
Cube root of
2e plus 2 by 3 f is equal to 1, right? So when you send this root 3 by 2 there, then you will get a contradiction. And how you will get a contradiction? So this is 2 by root 3, right? So this implies 2 by root 3 belongs to cube root
cube
of
root
2,
of 2 and
right?
omega
No, no, omega is not there.
only.
It's just cube root of 2 and cube root of 2 square. This is an arbitrary element of q adjoint with 2 uh, cube root of 2, right? Now this is there and
Contradiction here.
2 inverse is also there. So you can q is anyway there inside now, so you can divide by 2. So this will implies 1 by root 3 is inside uh, cube root of 2 and it is a field. So this will implies root 3 is inside this. Again the same thing will come, that will implies that q root 3 is inside this. And can it happen?
No, sir.
The same argument, right? The degree argument. Contradiction since your
Degree 2 and
q
degree 3.
degree 2 and degree 3. So even if you omit the real part comparison, still from the just by comparing the complex part, you will get. Okay, so this is a and 2 does not divides 3. So iota is also not there, right? So iota is not there and root 2 is not there. Then what can be the intersection? It is just q, because m dash is it was m was q adjoint with root 2 and iota, which is the smallest field containing root 2 and iota. If root 2 and iota is not there, then uh, only
Yes, sir. Fine.
possibility is q will be there. Just q will be there in the intersection. So intersection is q, and uh,
Q over Q.
So what is A option? A option says Q over Q is not normal. Means it is not the splitting field of a polynomial over Q.
Yes.
So this implies M intersection M over Q is nothing but Q over Q, which is trivially a normal extension. Why? Trivially, the trivial normal extension of Q. What polynomial you can take for which the splitting field is Q itself? See,
So, M
it is a splitting field of, it is the splitting field of splitting field of any polynomial of the form polynomial of the form x minus a, where a belongs to Q, right? What is the root of x minus a such that a belongs to Q? Just a, right? So where will be the, what is the smallest field containing a? That is Q itself, right?
Q.
So you can take any polynomial of the form x minus a and its splitting field is Q itself. So it's trivially a normal extension. And not just x minus a, you can take any polynomial which
Linear.
splits into linear factors over Q, right? So that's why option A was wrong, because it's a normal extension, and here they are saying it's not a normal extension. Now, as you said, second is correct, third is correct, and fourth is not. So let us just see why. The second option is M double dash is a normal extension, right? So what is the splitting field? Means what are the polynomials for which it is the splitting field? M double dash is adjoining all the four uh, elements. M double dash is Q adjoined with root 2 iota cube root of 2 cube root of 2 and omega. So it is a splitting field of, so you can take a collection of polynomials, right? Splitting field of uh, x cube minus 2 x square minus 2 over, not x square minus 2 x square. Okay, iota is also there, so you should take one more, or you can take simply uh, plus 2 here. It will also do your job, I guess. So what will be the root of this? This will be x square is equal to minus 2, and when you take the root will be plus minus root 2 iota, right? Or if you are confused by that, then simply take x cube minus 2, x square minus 2, and x square plus 1. This is also okay. What will be the roots of it? Its roots will be cube root of 2 times omega, and cube root of 2 omega square. So the smallest field containing it will be q adjoined with cube root of 2 and omega. And then you have root 2 and iota. So root 2 will come from here and iota will come from here. You can also take remove this part and then take x square plus 2. It will also give the same answer. The splitting field of this over Q. So this is normal. Normal extension means it's a splitting field of some collection of polynomials. Okay. Now why third one is correct? Third one is saying m over q. So m over q is just q adjoined with root 2 and iota, right? This is the splitting field of the last two polynomials, x square minus 2, x square plus 1. Or you can take uh, x square plus 2. Anything will work over q. This is again a normal extension. So that's why the third option is correct. And what is the fourth option? It is m dash over q. It's saying not normal, but it is actually a normal extension. So all these fours are normal extensions. So wherever it is not, the option is not correct. Okay. So m dash is cube root of 2 times cube root of 2 and omega adjoined with q, right? So D part is q cube root of 2 and omega, and it is the splitting field of which polynomial? X cube minus 2 over q. This will again imply normal extension, and the option is incorrect because there it is written not normal. Okay, correct? Clear, Vivek? Shall we move to the
Yes,
next
sir.
question? Okay. So here comes question number fifth. Choose all the correct options. Now it's about separable. Which extension is separable and which is not. X5 minus 1 is separable over field F9. So separable means
Having no multiple roots, I think.
in any extension. So it may not have a multiple root in the given field, but if it is separable, then it has no repeated roots in any extension of that field. Means not just in F9, but on any extension of F9
Extension.
also. So we saw something related to when it can have a repeated root or not. Some statements we have already seen. Na? Just write that again. So do you remember this theorem that uh, fx belongs to fx as repeated root in any has repeated roots uh, if and only if GCD of fx and
1.
d of fx is not equal to 1.
1. Not is equal to 1.
In case of repeated roots, it's not equal to 1. If it is 1, then we have no repeated roots. That means the polynomial is separable. So that will we will use. So let me just give them some name A, B, C, and D. So A1. So fx is x5 minus 1, and your d of fx is 5x square 5x4 plus
4.
5x4. So what is the GCD?
GCD is 1, I think.
You can check the GCD is 1 because it has roots to be just x equal to 0, and x equal to 0 is not a root of it. So here fx and dfx have 1, so they are separable. Fx is separable because it has no repeated roots in any extension. Second, fx equal to x5 minus 1. What is d of fx? This is 5x4, but we are over f5. So this is 0 in f5, right? Because 5 is 0, right? And this implies fx and dfx has GCD not equal to 1, right? So here fx is not separable. Same polynomial we have to check for f25. So f25 also have characteristic 5. So there also 5x4 will be 0. So this is same as B, right? And in D, uh, again they will be 5x4, and this is x minus 5, 1 plus x plus. So let me just write. So fx is x5 minus 5 equal to x minus 5, 1 plus x square plus x cube plus x4. And by existing criteria, we have seen that this is 4 is p minus 1, right? So 1 plus x on to x raised to p minus 1, this polynomial is reducible by existing criteria. So this is irreducible, and you have d of fx to be 5x4. So 1 is not a root, so x minus 1 is not a factor of this, and this is irreducible. So no other factor uh, can divide this. So this implies that their GCD is 1
1.
over q, and that means they are separable. Fx is separable over q. Yes, so I hope that's clear. Let me paste another question. Choose all correct options. Q adjoint with the ninth root of unity is a separable extension. What do you think? So one theorem we saw that if characteristic of the f is 0, and then any algebraic extension is a separable extension. So solution, if characteristic of f, that theorem is there in the lecture notes, equal to 0, then any algebraic extension of f is a separable extension. So with that, you can say A and C are correct because A is an algebraic extension. So this satisfies x9 minus 1 over q, right? And q just this adjoint with this. So this is an algebraic extension, and similarly here, uh, fourth root of root 3 satisfies x square minus root 3.
Sir,
Huh?
sir, here characteristics of f, that means only q for first.
Any characteristic f, any field with characteristic 0 will satisfy this property. So q has characteristic 0, right? Characteristic,
Yes.
uh, means uh, the number n such that
N times of elements such that you get,
n
I think,
times a
unity or zero.
n times a is 0 for all a inside field.
Yes.
The smallest such n, or that is equivalent to say that smallest n such that n dot 1 is equal to 0, because 1 generates everything. So n dot 1 equal to 0 means uh, so smallest n such that n congruent to 0 in that field. But in q, can it happen for any natural number
No, sir.
that n? No, right? So a characteristic is a natural number. If it is exists, then it's so we say it's the smallest natural number such that it happens. So it's a natural number by default. So if no characteristic field has no characteristic, then we say it is of characteristic 0. Okay,
And
so
then any algebraic extension of the field is, then we can say
separable.
algebra.
Then
Okay.
algebraic extension is a separable extension. So here Q is of characteristic 0. So and A and C are algebraic extensions. So they are separable extensions as well. Okay.
Okay.
Okay. And one side is always true that if it is a separable extension, then it is an algebraic extension, right? So this side, because this is how this separable extension was defined. It has any polynomial is said to be separable if it is uh, uh, what to say, in any extension it has no repeated roots. So that is when we say that a polynomial is separable. But in the definition of separable extension, we say that an extension is separable if it is first of all an algebraic extension, and then the minimal polynomial of each element is separable. So separable extensions are algebraic extensions, but the converse is true when the characteristic of f is 0. Okay, Vivek, does it make sense?
Yes, sir.
And by definition of separable extension
And sir, what about option B and
is,
D?
that's what we are doing. So by definition of separation extension, each separable extension is an algebraic extension. So A and C are uh, okay, because in characteristic of f equal to 0, you have if and only if condition, algebraic if and only if separable. So one direction is true by the definition of separable, but if characteristic of f is 0, then algebraic extensions are also separable, right? In general, it may not be true. So in option B, it is not an algebraic extension. In B, f5 adjoint with T is over f5 is not an algebraic extension, right? The polynomial ring, polynomial field of sorry, field of rational polynomials over f5. Because which polynomial T will satisfy? T is a variable, right? So T will not satisfy any polynomial. So f5T
Sir,
over f
sir, F5T contain any types of polynomial or
rest. Uh, see, this is a field of fractions. So you know how from an integral domain we generate we form a field of fractions.
Px upon Qx in the form of?
So you have say integral domain I, then you can form a field of fractions of I. It contains elements of the form a by b such that a b belongs to I and b is not equal to 0.
0.
And then you define addition and multiplication over this a by b over this setup such that it becomes a field. So that is a general form of forming a field from a integral domain.
Yes, sir.
So if f is a field, then fx is an integral domain. In fact, it's the principal ideal domain. Then the field of fractions of this integral domain, that is, you collect all elements of the form px upon qx such that the px and qx are inside are polynomials, and then you have qx non equal to 0, and you define the sum and multiplication same as this. So it has, so here the multiplication and sum are defined in the obvious way, that is ad plus cb upon bd, and then
BD.
multiplication is just acbd, ac upon bd, the usual way, and then it turns out that it becomes a field. And so this is the field of fractions, rational functions. Okay, px upon qx such that qx is not equal to 0, and the sum and uh, multiplication are defined in the usual way. Okay, so it's not just polynomials. It contains, of course, you can take qx to be 1, then what it will be just polynomial. So it contains all polynomials, but it contains more rational polynomials also it contains, because
Okay, sir.
that's how you will get inverse. Now how will you define how will you get the inverse of a polynomial if you just consider the ring of polynomials? This rational field allows you to get the inverse of that, because for any fx that is non-zero, you have 1 upon fx inside this field, such that, which is the inverse of fx.
In generally, it is a rational types of polynomials.
Rational types of rational polynomials. But
Oh,
I'm saying it's a more general setup. For any integral domain, you can generate a field.
okay,
That's
fine.
just by a upon b kind of elements you consider from the integral domain and define it in a usual way. Okay, so this is the field of fractions over f5. Is it's not algebraic because the polynomial t cannot satisfy any other polynomial. The it's actually variable, na? So it won't satisfy a polynomial in F5. So this is not algebraic, implies uh, it is not separable. Because for separable, you need algebraic first. B is this. And what about the C part? C is done. D part. So F3T is a perfect field, it's saying. So it's a field of characteristic 3. So I will use something that we have already, that you might have seen in the lecture videos. So it's saying it's a perfect field. So if F3T is a perfect field, then of course characteristic you have finite of characteristic 3, then here you have, then for such a field, every irreducible polynomial is separable. But from lecture notes, I won't go to the proof of it. You can see the lecture notes. We know that the polynomial x cube minus t. So now t is an element of f3t, right? So this x cube minus t is a polynomial with coefficients in f3t, polynomial in x. Here t you will consider as an element of f3t. So this is an element of this field f3t and its polynomial ring. So this polynomial is irreducible. Is irreducible but not separable. If it is perfect, then every irreducible polynomial has to be separable. But it says if it is x cube minus t, this polynomial is irreducible but not separable. So this implies f3t is not a perfect field because it violates the necessary condition for a field to be perfect. Okay, hope it's clear. Shall we move to the next question? Now here come questions on Galois extensions. So maybe we should uh, add a new page. That would be good. To make it small. So it's visible, right?
Yes, sir.
Okay. So what's the Galois extension?
Sir, collection of all automorphisms.
So any algebraic extension of a field, we say that it's a Galois extension if it is normal and separable. And separable is by default algebraic, so you can say any extension that is normal plus separable, we say that it's a Galois extension. So this is nothing but normal plus separable. So here you have to see the both of these things. Yes, the splitting field of this polynomial is a Galois extension over Q. What you say, whether it is a Galois extension or not. So
Sir, Galois, that means the polynomial
norm
should be irreducible, first of all.
not necessarily. Galois means just normal plus separable. A separable extension that is normal also.
Okay.
Reducible, you don't need na. It just uh, what if it has
That's
two
great.
roots? X minus uh, say if I take not just two roots, it has to be separable. So single root, but it can be reducible also. Say you can here if you take this polynomial that we were discussing earlier. Yes, so this m dash. If you take the polynomial x cube uh, x cube minus 2 and x square plus 1 over q, it's reducible, right? It has two
No,
factors, right?
sir.
It is reducible, and m dash is an extension of it. So it's a splitting field, it's a normal extension, and all its roots are distinct. It has iota minus iota, and then 2 root cube root of 2 cube root of 2 times omega cube root of 2 times omega means uh, yes, omega square. So it has distinct roots, and it is separable plus normal, so it's a Galois extension.
Okay.
The theorem is a bit in case of okay, so in case of perfect fields, you need that every irreducible polynomial is separable. But here it is fine. So normal plus separable that you want to check. So normal splitting field is given. That implies normal is there, because normal just says that it is a splitting field of something, and splitting field is by default algebraic extension, right? Splitting field means it contains the roots of certain all roots of certain polynomials, right? So it is by default an algebraic extension. And then Q, it has characteristic 0. So on characteristic of f equal to 0, any algebraic extension is a separable extension, right? So this plus this will give you what? That this is separable as well, and hence non-Galois, right? Because normal and separable both you are getting. Clear? So this option is correct. We need not to do anything. Just whatever is written in the question, that is good enough. Okay. So what about the second part? F25 over F5 is a Galois extension. Okay, Bob, can you say something about the C part, whether it's Galois? So one thing is clear, right? It is characteristic zero and algebraic. Characteristic,
Sir, C contains splitting field, I think, over Qi.
no. So separable is fine, right? Characteristic zero plus algebraic.
Yes.
Normal it is not, because uh, uh, fourth root of 2 satisfies. Oh, normal is also there because it is a splitting field of, yes, you are right, splitting field of, because iota is there, na? I didn't see iota.
Yes.
Splitting
X4
field of
minus 2.
x4 minus 2. This implies normal as well. So this is correct. It is Galois. This implies Galois extension. And what about last one? That we have already seen that it is not algebraic, right? This extension is not algebraic. This is not algebraic, which implies not separable, and which implies not Galois, right? Now, what can you say about the second one? It's correct or not?
Sir, F25 over F5, that means contains
Hmm? F25 over?
F5
Hmm?
contains only uh, elements, na? That means there does not exist any types of polynomial.
Oh, it's an extension of F5, right? And how like extensions of a finite field was defined? There is
But yes, sir, yeah.
some garbage is there. So in the in the set that is posted on the website, they have written F5 over F25 over F5, and in the solution that they have posted, they have written F5T over F5T square. So we will go with the one that is being posted over the website. Okay. So F25 over F5. That's a Galois extension or not? see how the extensions of, so for B, FPN is a Galois extension of FP, because uh, F F FPN is what? FPN is the splitting field of which polynomial? TPN minus T over FP. That is how this was defined, right? You remember how the finite fields were defined? The construction of finite field in I think week 3 or 4. It's somewhere it was there.
Yes, sir.
Maybe
And I think degree is
I can tell you the lecture uh, also. Let me just see the notes. So this is how the construction of finite field was discussed, if you remember. So any field of order p raised to n, uh, uh, you construct it just as a root of tpn minus t. It's coming.
yes, sir.
It's
And
very
I think there's contain distinct roots. All have distinct roots.
all have distinct roots. So it is splitting field because you have uh, this thing, the uh, root, the polynomial tpn minus t, it contains all the roots of this polynomial. So and it is separable because all
Unrepeated.
the roots
Yes,
are,
distinct, not
see,
repeated roots.
if the roots are not distinct, then its cardinality will reduce, right? That's
Yes,
also a cross verification kind of thing. So its cardinality is pn, that means all roots are distinct, right?
fine, sir.
So this is how the finite field were constructed. So can you see my screen or
No,
it's
sir.
gone? It's gone. Oh, I don't know what happened. Let me just reshare it. Is it visible now?
Yes, sir.
Okay. So yeah, that's what I'm saying. This is a Galois extension of FP because FPN is the splitting field of TPN minus T over FP. I couldn't find the lecture. Otherwise, I would have tell you which theorem is this. But I think you remember now that something like that we have done.
Yes, sir. Fine.
I think this is a lecture. Existence theorem for finite field. Yeah, this is. So this is like lecture 6 of I think week 2 or 3, week 2 probably. So there they have mentioned the theorem that uh, existence theorem for finite fields, and there they have if p be any prime and n greater than equal to 1, then there exists a field of order p raised to n. In that theorem, the proof is they consider the polynomial tpn minus t over fpt, and then this polynomial has distinct roots because if you take the derivative of it and its GCD with the the original polynomial is 1, so all the roots are distinct, and the splitting field will have uh, the splitting field will have all distinct roots, and it the collection of all distinct root actually forms a field. That is the idea of the theorem. So by that theorem you can, so screen sharing is paused, it's returning. Okay. Okay.
Visible, sir. It is visible.
Okay. So clear, like Vivek? You can just go back to that lecture and see. So it's
Sure,
the
sir.
splitting field, and uh, it contains distinct roots, and it contains all. Uh, okay, just a second. And all the roots are distinct. So you are submitting assignments or not? Okay.
Yes, sir. Last assignment or before?
Not submitted. So you are supposed.
Last one is remaining, sir.
Okay. So the deadline has not gone, I guess, right?
Yeah, tomorrow is the last.
Okay. Okay. So uh, fine. All options. This is a Galois extension. So let me paste the next question. Uh-oh. Yeah. So it's a true false question. Let me just enlarge it a bit. So it says K, let K be the field of characteristic P, where P is a prime. Consider the following two statements. Uh, Fx belongs to Fx satisfies df equal to 0 if and only if fx equal to gxp for some gx belongs to kx. And the second is, suppose k equal to fpn for some n belongs to n, then fx belongs to kx satisfies df equal to 0 if and only if fx equal to hxp for some hx belongs to kx. So yeah, let us check the validity of these statements. Solution number 1 says fx belongs to fx satisfies df equal to 0. So let fx be a polynomial of the form an xn plus an minus 1 xn minus 1 dot a1x plus a naught. Then what is df of x? This will be an xn plus n minus 1 an minus 1 xn minus 1 plus a1, right? Now what it says that df equal to 0. So uh, df is equal to 0 means d of fx is equal to 0 if and only if all these coefficients are 0, means, right, n is equal to 0, sorry,
And an
uh, yeah, and an and minus 1
one, n minus one,
an minus 1 and
a1.
let me just say For 2, what is this? This is 2 times A2, and then A1. This is all, these are all equal to 0,
Okay.
right? So uh, this implies, and you are in congruent to 0 mod p. You are in a finite field, right? So that means that p divides I ai for all I, right? But uh, if I is, this is a prime, so this implies this is if and only if p divides I or p divides ai. A prime dividing a product means either one is divisible by that or the second one is divisible by that, right? So I should write it more clearly. So it is ai. So either p divides I or p divides ai for all I.
Sir, first statement that uh,
So if p,
that
yeah,
that you have write down, and the second is, sir, your second line, first line, and after that second d of fx.
hmm,
N a n x n minus one. I think here will be no? n n minus one, n minus two.
yes, yes, yes. This will be n minus 1, n minus 2, although it won't create a difference in the calculation, but yes, n minus 2 and so on. Okay, thank you. So the rest things will be same. So if p divides ai, that means uh, that part is 0, right? ai equal to congruent to 0 mod p. That wise in this, that means that in this polynomial, that part is not there, right?
Yes, sir. Fine.
And so only uh, non-zero coefficients are for, that means that if p does not divides I, then p must divides ai, and which implies that p ai congruent to 0 mod p. So this is if and only if the non-zero uh, coefficients corresponds to I which is corresponds to i's which are divisible by p. So if some index is not divisible by p, then its coefficient has to be 0, right? So this says now if p does not divide I, then the coefficient should be 0. So non-zero coefficient must correspond to the i's which are divisible by p. That means you have uh, fx to be uh, a naught uh, will be there if and only if fx is just a naught plus you have ap x raised to p plus ap square x raised to p square and dot some a p raised to r x raised to pr, right? Because Now the indices, the non-zero coefficient corresponds to those indices only which are divisible by p. So you just have those non-zero coefficients. This may be zero or non-zero, we don't know, but non-zero others are zero, that we know by this. So if p does not divide I, then p divides ai, and then ai equal to 0. Clear, Vivek?
Yes, sir. I think last line has some issue.
So see, it says p divides ai for all I. So either p divides I or p divides ai. So if p does not divide I, then p has to divide ai, right? It divides one of them. So if it is not
Okay,
dividing
okay,
one,
okay, right. Sir,
so
fine, fine, complete.
p divides ai, then ai is 0 mod p. So if I is not is not divisible by p, then it has to be uh,
In the form of p raised to n.
yes, something I did wrong.
Okay.
It need not be of the form p raised to n. Sorry, it is divisible by p. So it may be some n times p also, right? It is
Hmm.
just some, may not be a power of p, but just it must be divisible by p, right?
Okay.
And what does this mean? That this means that this is g of,
The form
that is
of xp.
all g of xp, where xp is g of xp, where gx is a naught plus uh, ap plus apx, sorry, apx plus a 2p x square and dot 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 a rp x raised to r. And this is inside your kx or fx, which notation it is kx. The first statement is correct.
Sir,
Yes.
sir, if characteristic is suppose p that is given.
Hmm.
So if we write here p raised to n or np, both will be same.
No, 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 no. See, in characteristic 2, let's say in F7,
Hmm.
2, uh, 2.3 is 6, while 2 raised to 3 is 8,
8,
which is 1.
1.
They are distinct elements, right? 6 is not same
Okay,
as
sir.
1. Okay, now the second statement is, suppose k is some power of uh, some extension of fx belongs to kx, then df equal to 0 if and only if fx equal to hxp or some hx belongs to kx. So second statement also we can see. So this is a more general statement. Uh, Not, I will say general, but here k was any field of characteristic p, may not be finite also, right? And here we are restricting ourselves to finite fields. So it contains a small family of fields. Oh, oh, mm, just a minute. Yeah. So yes. So for second part, uh, first of all, both are true. So let me mark that. So it says k is fpn, then um, fx belongs to kx if it is satisfies df equal to 0, if and only if fx is some polynomial raised to p. Now, if it is a finite field, then you have one more condition. If k is just fpn, then k is a perfect field, right? And uh, then perfect field means the pth power map that I a goes to a raised to p. This map is surjective. A field is perfect if the map a going to a raised to p is surjective. So, and any field of and these fields are perfect fields that we have seen. So it is a perfect field means, okay. So let me again write, let fx is equal to I, using the same notation, right? Fx is using for polynomial, and then he want to show it to be some power of p. Okay, let fx is a naught plus a1 x plus dot 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 some an xn, right? So I should write k. Okay, so then for each ai belongs to k, there exists
Perfect field.
bi belongs to k such that, as it is perfect, so the point map is surjective, such that bi raised to p is equal to ai. Yes, you want to say something?
Sir, can we write here like that as you earlier uh, mentioned x raised to pn minus x type?
Yes, yes, you can take that also. That we will use
Okay,
actually.
and also has distinct root for that
You,
polynomial.
no, 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 no. Distinct thing. I don't think it's needed. No. So what I want to do is
Or perfect, sir. It is a perfect, so I am telling you. If
irreducible roots are elements have distinct roots in perfect.
yes,
Irreducible polynomials are separable, but not a general polynomial. So what I am trying to do is, you have this, then from from 1 you can write fx to be just, you just take those where uh, it is divisible by rp, x is to rp. Yes, I should write, yeah. And then, so you use this perfectness also for each ai belongs to k, there is just bi such that bi raised to p is ai, and this is happening since k is perfect. So the pth power map is surjective. Then you replace this ais by uh, this bi raised to p, a naught plus this a naught is required. Yes, maybe this is b naught uh, p plus bp raised to p xp dot plus b to p. This is just an index raised to p, x to p, so on to b r p raised to rp, x raised to r of p, and then you take, so you can take a common power because they have the same power, bpx raised to p plus b 2px raised to 2p, and then dot 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 You have B RP x raised to R of P. Or maybe just taking this P out is good enough. You can put x square inside and this R also inside. We just wanted to take this P out. Now what, Vivek? We wanted to make some pth power.
Yes, sir. It's like
Yes.
look like a polynomial of degree p.
What is your hx now?
Hx will be this, sir.
So
BRPXR power p sigma.
since since k is of uh, characteristic P, characteristic P, we have this to be equal to uh, B naught plus BPX plus B 2P. I'm writing this X like that. BP times X raised to X square dot BRP X raised to R, and whole power you can take to be P. Why? Because if you expand it, so other terms will have will have coefficients multiple of p, all multiple of p. For example, if you expand x plus y square, this is what, this is x square plus y square plus 2x, right? So this 2 comes, and if you expand x plus y plus z square, then you will get x square plus y square plus z square plus 2xy plus 2yz plus 2zx. This comes. Similarly, if you can see, if you expand, say, 4 terms, then again x square plus y square plus z square. Not just square, you can take any power p or n. The coefficient here will come, which is a multiple of n, except those powers. There you can take some n outside common, and then something will remain. And this n, as you are taking here p, so this will be some p and times something. So this part will vanish, and only this part will be there, the powers part. That's what we are doing. You take its power, it will be b naught p, bp xp, b2p x square p, and then brp xrp. And something will come, something p times something will come, and as the characteristic is p, so this part will vanish. Okay,
Yes, sir.
clear?
Fine.
So this is your hx. This is equal to hx raised to p for hx. So why we need k to be fpn? Why not a general field of characteristic p? In part one we have a field of any field of characteristic p, na? So why in part two we need field to be just finite field of order p raised to n? To use the perfectness. These fields are perfect, but in general, any field of characteristic P may not be perfect. Okay, but FPN are, they are perfect. So they are perfect. That's why we could replace A naught by some PHP, some powers, some PH powers, and that PH powers are crucial so that we can take a common power P outside, right? And then we can do this. Okay. Okay. So. I thought I could have, I will do the assignment 5 also, but time just here 20-25 minutes. We are left with two more questions. Let me just quickly wind this assignment. Na? I'm pasting next question. This one is fine, right? Any doubt?
No, sir, done.
Okay. So let K denote the algebraic closure of Q, then K over Q is a Galois extension. Yes. So is it true that it's a Galois extension? So algebraic extension, it is there, right? Because it's an algebraic closure. So characteristic is 0 plus algebraic extension. This implies separable is there. Right? What about normal? So by definition, it's normal. Right? It's the algebraic closure. It is the smallest field containing all the roots of all polynomials of Q. So you collect all the polynomials in Q and then it is the splitting field of that. Or there was an equivalent condition of being normal that for any alpha belongs to K, minimal polynomial of alpha. This is an equivalent condition of normality. Minimal polynomial of alpha over polynomial of alpha over Q has all the roots in K, right? Because it has all roots of all the polynomials. So for any alpha, whatever is the minimal polynomial, all roots will lie inside the algebraic closure, right? So thus it is also normal. And this implies that it is Galois. So this is true, right? Let me just paste the last question. Now here comes what if we take uh, a finite field, whether its algebraic closure is a Galois extension, because now we cannot use the characteristic zero thing. So similarly, similar to question number 9, it is normal. That is correct, right? Because again, if you take for any alpha, the minimal polynomial and all its roots are there, so it is normal. What about the separable part? So for perfect field also, so since uh, FP is a perfect field of characteristic uh, since FP is a perfect field of characteristic P, uh, all its algebraic extensions are separable. That's again a statement discussed in lecture notes. So as now as uh, K is an algebraic extension, of course, algebraic extension of FP. This implies so as K is an algebraic extension of FP, so this implies K is separable. K is an separable extension. Yes, and thus it is a real extension. Yeah, I hope that is okay. We can start assignment number 5 straight away. So it is fine, right, Vivek? Or any doubt is there? So assignment number 4.
No, sir, complete.
So let us start assignment number 5. Forget to write assignment number 4 here. Okay, so I will just paste uh, assignment number 5. First question. Is we can uh, discuss for I think 15 to 20 more minutes. Let's try to finish as much as we can do today. So it says let K be a field. Suppose S is a subgroup of automorphism of K, which is isomorphic to S3. If KH is a fixed field of H, what is the uh, degree of K over KH? So have you gone through the lecture notes of this lecture this week? So what is KH? This notation means the set of A belongs to K such that sigma of A is equal to A for all A belongs to, so for all sigma belongs to H, means those elements of K which are fixed by all the automorphisms inside this subgroup H. Okay, the fixed field with respect to this subgroup of automorphisms. So Yes. And Artin's theorem says that, let me just write it here. Artin's theorem says, let K be a field and this is any subgroup of K, and with the condition that it is a finite subgroup. So then you have the dimension of K over KH. So this is of course a subfield of K, right? Similarly, if A is fixed, B is fixed, then A plus B is fixed, and A minus B is fixed, A B inverse is fixed, because sigma is a field automorphism, right? So it's a subfield that is easy to check. So the dimension of this K, so K is an extension of this subfield, right? So dimension of this K over KH is same as the order of, oh, I have misused, means this, overused this notation H. So this is K, this symbol. So here our uh, subgroup is H, which is isomorphic to the S3. So the degree is, since in H is isomorphic to S3, order of H is less than infinite, which is uh, just order of H is just 6. Na? It is just 6, which is a finite number, and therefore directly applying the Artin's theorem, you get K over KH has degree equal to order of H, and that is 6. Right? Clear? It's very easy. Just you apply the theorem and you will get. Fine. Let me go to the
Yes,
next
sir.
question. Next question says that K be a field. Suppose H is a finite subgroup of odd K, and let F is the fixed field with respect to the subgroup H. Choose all the correct options. Let me just take out my charger. Yeah. Any uh, idea? So, if you have gone through the notes of this this week, the week number 5, then there was again a theorem. Just by applying that theorem, it's become all options you can directly see. So what is that theorem? Let me just write it, and then theorem says it's just a application of that theorem, direct implication. The theorem says let K be any field and this is a finite subgroup of the of K. Then you have first this uh, K over K of this is to be a finite Galois extension, and with that the order of automorphism group of K over Kf, this is nothing but just this. Okay. Uh, so this directly gives that A, B, C, and D all are correct, because first one says separable. Galois means normal plus separable. So Galois is there, the normal, separable. These three are correct, and then the fourth one is just this, right? F is K, fixed field of K, H, right? So this is just notation. So A, B, this gives A, B, C, and D all are correct. Okay, let me write one or two more, and then we will stop. So what that question is saying? It says let F1 and F2 be okay. Let me go just paste first. So let F1 and F2 are Q automorphisms. Q automorphism means it fixes Q of uh, automorphism of the field Q root 3 such that it fixes root 2 and root 3, and let F1 is same F1 root 2 is same as F2 root 2, and F1 root 3 is same as F2 root 3. Then one has to choose all the correct options. First one is F1 is same as F2. So
So
what is
Q automorphism, that means?
Q automorphisms means it fixes Q, all elements of the Q. So it is an automorphism of Q root 3 root Q. Okay, so this is a extension of Q, right? So our automorphism, an automorphism, not an auto. Say F belongs to part of Q root 2 root 3. I will just write like that. Is said to be a, in general you can say that if K is an extension of F, then any automorphism of K is said to be an of F automorphism. So said to be a Q automorphism here because the base field is Q. Q automorphism if F of A is equal to A for all A belongs to Q, right? Means it fixes all elements of Q. That's it. So now what is Q root 2 root 3? This is nothing but A plus B root
C root
2,
2, C root 3
yeah, C root 3 and
plus D 2 root 3.
D root 6, right? Root 2 root 3 is root 6. I'm just writing like that. Right. So it says F1, F2 are Q automorphisms. So F1 and F2 are Q automorphisms. Implies F1 of alpha equal to F2 of alpha for all alpha inside Q, right? And they are also fixing root 2 and root 3. And second thing is F1 root 2 is F2 root 2, and you have F3 root 3 to be F1 root 3 is F2 root 3. They are fixing root 2 and root 3 also. So what that mean? That they are fixing Q and also root 2 and root 3. So this will implies that they are exactly the same, because this will implies F1 of A plus B root 2 plus C root 3 plus D root 6. I can write it more with more clarity. This implies for any A, B, C, D inside Q, we have F1 of A plus B root 2 plus C root 3 plus D root 6 is F1A plus, so it's an automorphism, so it will uh, split in addition and multiplication both, right? F1 root 2 plus F1C F1 root 3, and then you have F1D F1 root 2 F1 root 3. Right now F1A is same as F2B because it's a rational number, and then uh, F1B is same as F2B, F1 root 2 is same as F2 root 2. Same here, everything is same for F2 as well. This will be same as saying that F2 of A plus B root 2 plus C root 3 plus D of root 6. This implies F1 and F2 are same, right? So first one is same, second one is same, first is true, second is not, third is both F1 and F2 must be the identity map. So that's need not be true, because uh, uh, we can ha have F1 equal to F2 such that F1 of root 2 is equal to minus of root 2, and F2 of, oh sorry, is equal to F2 of root 2. They have the same value as root 2, but not exactly as root 2. And F1 of F2 of root 3, same as minus of root 3. So because there is a, so in that case also they are same, right? They are having the same value at root 2, they are having the same value at root 3, and they are having, of course, uh, uh, same they fixes all elements of Q. So they are the same elements, but this implies that they are not equal to the identity map on K, right? Because root 2 is mapped to root minus root 2 and root 3 is mapped to root minus root 3. Even you can take one to be the same, root 3 can be mapped to root 3. Still, you if you take root 2 mapping to minus root 2, then it will also work. So this is not needed that F1, F2 are identity map. It doesn't guarantee that. The example that is given in the solution, that is wrong, because there they have sent root 2 to root 3 and root 3 to root 2, if I am not wrong. But this example is not correct. Can you tell me why? We cannot have this f1 like that, root 2 map. Still, if it is a valid example, then it is okay now, because root 2, the f1 and f2 both are having the same image at uh, same image of root 2, that is root 3, and same image of root 3, that is root 2. But such a uh, such q automorphisms are not possible. Can you tell me why? It it will say f1 equal to f2, but they won't be q automorphisms. Any idea, Vivek?
Sorry, sir.
No.
Okay.
So see, one thing we saw that if f is a q automorphism or f of automorphism, say in the base field, then if alpha is a root of some polynomial gx, then what I mean that, say if f belongs to some automorphism of k and alpha is a root of some polynomial gx, then f of alpha is also a root of gx, right? This is very easy to see, and we have already, this is also there in the lecture note. Oh, sorry, this is g of yes, because see, if gx is not say a naught plus a1x plus dot 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 an xn, and if alpha is satisfying this, that means g of alpha, that is a naught plus a1 alpha plus dot 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 an alpha n is 0, right? So if you just apply the automorphism, if f is making you confused, then you can take phi also. Sometimes we use f for automorphism, I mean sometimes for function also, but here we are taking it as an automorphism. So what is g of alpha? So this is use f a naught. Of course, this is base field preserving automorphism, right? So then f of a1, f of alpha, and dot dot dot, you have f of an and f of alpha raised to n equal to f of 0 is 0, right? But it is base preserving, so this will be nothing but a naught plus f of a1 is a1 f of alpha dot dot dot, here f of an is again an, and then you have f of alpha n equal to 0, and this means that g of f of alpha is equal to 0. You are just replacing x by f of alpha. So if alpha is a root, then f of alpha is also a root. Clear? So this is a corollary of means an application, you can say. Now, why this is not a, why these polynomials, why these maps are not uh, q automorphisms? Because if it is a root of q automorphism, then x square minus 2 root 2 satisfies this, right? But f1 root 2, that is root 3, does not satisfy this, right? Root 3 is not a solution of this. So you cannot send root 2 to root 3 and root 3 to root 2. This is a wrong assignment of elements if it is a Q automorphism. That's why I defined root 2. I send root 2 to minus root 2 because whatever polynomial is satisfied by root 2 over Q minus root 2 will also satisfy that. And whatever polynomial root 3 satisfy over uh, Q minus root 3 will also satisfy, because the minimal polynomial of root 2 is x square minus 2, and minus root 2 is also a root of that, and minimal polynomial of root 3 is x square minus 3, and minus root 3 is also this. If minimal polynomial is satisfied, then any polynomial satisfied by root 2 will also be satisfied. Okay, so this is a correct assignment. This was not. So this was a mistake in the solution. I haven't prepared it. Means I saw that it is posted, and I noticed it, so I thought that it should be cleared. Okay. So I think we are done with the time. I thought that I would have finished this, but okay then. So uh, maybe we can stop here if you don't have any other doubt, Vivek.
No, sir. And
Oh, okay. So we will do the remaining questions and hopefully start solution of the assignment 6 as well in the next interaction. Okay.
okay, sir.
Okay. Let me then stop it here.
Yeah.